Today we're going to talk about convolutional neural networks. Convolutional neural networks are a form of neural networks, but as opposed to some of the fully connected neural networks, which we discussed in the previous lecture, they're going to alleviate a number of issues that happen there. So yeah, let's start by talking about why do we need something beyond fully connected layers. And often called FC layers, fully connected. The problem is when you deal with fully connected layers, you have that the parameters grow very, very fast as you have more and more layers and as you have more hidden neurons. So let me give you a simple example just to do a back of the envelope calculation on how things will be going. So let's suppose we wanted to do some sort of image classification using a fully connected neural network. So what would that look like? If we tried to do well, first of all, what is our input? So our input would be an image, of course, because we want to classify, well, sorry, let me define what image classification means. It's pretty intuitive, but given an image of something, you want to classify what it is. For example, if you're given a picture of either a cat or a dog, you want to classify whether it's a cat or a dog. So our input is, of course, an image. And how big is this image? Let's say, as an example, a reasonable sized image that we could give would be, say, a 1 megapixel image. You know, a fairly small picture in terms of what your camera can take nowadays, your phone can take nowadays, which is about like, not about actually, this is, well, it depends on how you count. This is something like 10 to the 6th dimensional. And why is that? Because each pixel, yeah, this means 1 million pixels, and each pixel is one value. So you can think of an image, a 1 megapixel image, as a 10 to the 6th dimensional input. So fairly sizable. Now let's suppose we want to use the following, say, fully connected, the following fully connected architecture. We just have the input, and we had a hidden layer here, which is, say, much smaller. And we just made this a fully connected layer here. So the question is, what would we do? Well, how big would this hidden layer be? Well, a reasonable size hidden layer, if we're having such a high dimensional input, it wouldn't be out of line to have a hidden layer here, which is, say, let's say this is 1,000 hidden layers. Say 1,000, not 1,000 hidden layers, 1,000 neurons. Well, if we had 1,000 neurons, then how many parameters would there be here? Each parameter, remember that each edge here has to have a weight. So therefore, the number of parameters in this very simple model here, there's other things we have too, like including biases, and also converting from this hidden layer to taking some sort of, to converting to some output or something. But just for the single layer here, which connects a 1 megapixel image to a 1,000 neuron hidden layer, how many parameters would this have? It would have exactly one for each edge here. And how many edges are there? Well, it's just the number of inputs times the number of outputs, because each pair is connected. That would be 10 to the 6 times 10 to the 3, which is equal to 1 billion parameters. That's, you might not know how to like measure the scale of these things, but let me tell you that is a lot of parameters. As one example that's been in the news is GPT-3. GPT-3 is bigger, but GPT-2 is a big language model, which has, this can do like state-of-the-art in terms of natural language processing tasks. So that has roughly 1.5 billion parameters. And yeah, it can do very, very complex tasks, whereas we're only trying to do a very simple task here in terms of like identifying whether an image is a cat or a dog. So you think somehow we're not being very parameter efficient here. Somehow we have way more parameter than you need for this task. And GPT-2 trains, or the amount of money that it cost to train this was probably in the hundreds of thousands of dollars in terms of the best estimate. So it seems like if this is what it really cost to do such basic tasks like classifying a single image, then probably machine learning wouldn't really be worth it in terms of cost. So yeah, something is wrong here. What is really bad about a 1 billion parameter model? Like, so what if it's that big? Well, there's a few things. One thing I already said is there's a huge cost to train. and huge cost in the sense that both in terms of time as well as money, yeah, it would cost a lot of time as well as money. It would probably need lots of data. In terms of when you have such a big model with so many parameters, often you need much more data in order to be able to optimize. Yeah, there's difficulties, sort of related, there's difficulties with optimization. It might be hard to get to any sort of good solution. And again, related, it would likely overfit, because we'd probably have many more parameters. Yeah, we just have a ton of parameters, which is often likely to overfit. So yeah, the question is, do we really need this many parameters? Maybe we it seems, I've kind of hinted at this whole time, we really did something wrong by just using this naive structure here, which connects every pixel of the input to every pixel of this hidden layer, or every neuron in this hidden layer. So really, something is going wrong. And the reason why is because if this was a general problem, then maybe that would really be necessary. Maybe if we didn't know anything about what we were doing and it was just some arbitrary input, which may be 1,000,000 dimensional, then that is indeed what we would need, because it could be a very complex structure. But the thing is, pictures aren't really that complex, right? You and I can recognize images very, very easily, compared to how we'd be able to do with a very abstract looking 1,000,000 dimensional feature vector. So let me show you what I mean by that. Like, there's some principles which we can use. So here is a picture of a panda. And there's a few things which are important about pictures, natural images, which will be very useful in terms of our when we design something here. So one thing is that it doesn't really matter where in a picture something is. It's still a panda. For example, if I guess I don't know, I can't really move it, but suppose this picture of this panda was over at the top left here, or at the top right here, or bottom right, bottom left. It's in the middle. But no matter where in the picture it is, we would still say, okay, that's a picture of a panda. So one thing we have is something known as translation invariance. So this tells us the kind of principle here is that it doesn't really matter where in the picture the object is, it's still the same picture. And therefore the principle that we take from that is that early layers of the network, they should behave similarly in terms of how they respond to things in the image. For example, what I mean by that is, suppose you have a cluster of like edges, a bunch of edges which look at this area and they maybe go to some hidden layer. Then whatever you do there in the first layer, the weights should be pretty much the same thing as you have for the weights which connect to from here. Because if you saw the panda here versus if you saw the panda here, we'd want kind of the same response. So really, yeah, no matter, this kind of says that early layers, you kind of need the same parameters in multiple places. That might be a few too many leaps, but we'll talk about that a bit more as we progress. The second thing is that something known as locality. And this means that pixels near each other are really the ones which we care about. For example, when I'm trying to identify a panda, think really about how you recognize that this is a panda. What you might look for is the fact that you have these two black eyes which are close to each other, and then you have like this nose and this face, and it's like white here, and then you see the ears over here. So the idea is somehow the pixels which are closest to each other are very important. For example, we don't need to look at this pixel right here and then this pixel over here to recognize as a panda. Somehow we're looking at things which are close in space in order to identify whether there's a panda or not. So somehow we want our neural network to somehow have connections and only need to look at nearby pixels to each other. So these two ideas here will translate into two principles when we're doing neural network design. These principles are the following. They are parameter sharing, as well as only local edges. I guess that's not really, it's not really clear what I mean by that, but we want our edges to be local in some way. And I'll sort of, first of all, I'm going to give a simple example to try to show you what I mean by this, but we'll be a bit more precise a little bit later in terms of how what we're doing. Okay, so here's a simple example that will illustrate both of these two things in action, and it'll show you how for a very simple type of neural network we'll be able to do much better than what a fully connected network would get. So okay, I'm going to be very, very simple, like I said. So this left half here is going to be the input. And we're pretending our input is just a 5-dimensional object. So the way you should think about this, I'm not going to draw something much more complicated, but think of this left half as being like a 5 pixel image, and it's a 1D image. So it's really, it's a line, but yeah, think of this as a picture, and maybe you'd say that this and this are next to each other. These 2 pixels are adjacent to each other, and these 2 pixels are far from each other. So just think of this like a picture, just 5 pixels in a row. It's a very simple picture, of course, but it's going to at least get the idea across for what we're going to try to do here. So let's look at the most basic thing first. Like this is the fully connected, and we would just connect everything to each other. And yeah, I'm not going to draw all the edges. These are all connected, let's say. So anyway, that's the sort of simple fully connected. And how many parameters does this have? This has, very easy to count, 5 by 5 params, which is 25 parameters. But now, like I said, somehow the sort of first principle that we're going to use is the fact that locality. We care only about pixels of the input which are close to each other when we're making decisions. So in other words, we aren't going to connect, there's no, in some sense, there's no reason for this neuron over here to simultaneously look at this neuron as well, this pixel of the input as well as this pixel of the input, because somehow they're very far from each other. So you don't necessarily need to look at both of them at the same time, because you won't learn anything from them simultaneously. So what we're going to do is we're going to modify this to only look at local edges. We're just going to drop several of these edges, and that'll make it better. That'll reduce the number of parameters. So let's just draw the input and the hidden layer again. And now let's say each of these only depends on, each of the outputs only depends on a 3 neighborhood of pixels, so of the input. So for example, this is a good one to look at. See this one, rather than being connected to all 5 inputs, now it's only going to be connected to the 3 which are next to each other and kind of across from it. And we're just going to keep doing that here. And again, the principle that I'm trying to get across here is the fact that when we're making decisions, we only need to look at the parts of the input which are close to each other. See this guy over here, this neuron here, only looks at the bottom 2 pixels. It doesn't need to look at the one which is very far away. So this, by only having local edges, we already reduced the number of parameters, and if you count them, we only have 13 params. Now, the final simplification, which will reduce the number of parameters even more dramatically, is going to be parameter sharing, which may be a little bit less intuitive. But again, this is going to be based on the principle that, remember, it doesn't really matter which part of the image we look at. We want to react to the same thing. For example, we want to react the same way. Just to sort of emphasize that, suppose we had like a pattern in the input which was 1, 1, 0 here, and maybe we were trying to find like the image which looks like 1, 1, 0, then that would be kind of the same thing as if we would think it would be the same as we saw 1, 1, 0 over here. That's kind of what we want. Hopefully that's clear. Like I'm kind of using 1, 1, 0 here as a substring as something which sort of represents what a panda would look like in this higher dimensional thing. So we kind of want to react the same whether we see it over on this side of the image versus this side of the image. So what we'll do there is, as a result, we will then use the same weights, in fact, for different parts of the network. So let me sort of use some colors here. So every time I use the same color, that means that the weight is going to be shared there. That you can see all of these orange edges here have the same parameter, so those all are going to just be one weight. Then here we will have these blue ones. These are going to be a second weight. And then let's pick a third color. I don't know, pink, I guess, for something that stands out. This one will be a third weight. So you can see here what we did was basically this pixel, this neuron in the hidden layer here, let me use the color, this neuron in the hidden layer here, that is going to respond to an input which is in these three inputs here. It responds in the exact same way that we would have this neuron reacting to these three inputs right here. And the reason is because if these are the same, well, like I said, we're going to have these weights, the pink, orange, and blue one being the same. So therefore, we just go in and give the exact same value here as if you put the input on these bottom three and it went to here. So hopefully that makes sense. You're really just saying that you're enforcing certain edge weights to be the same. And since we have three colors here, well, this reduces it to 3 parameters. So you can see we started with 25 parameters, but through these two sort of principles, we reduced it all the way down to just 3, which is a lot more efficient for reasons we discussed above. Good. So that's the general principle. Let's start getting into what it actually means to be, yeah, is there something else I want to say here? No, that's it for now. Okay, so let's go on to this. These are the principles behind how convolutional neural networks are going to save us a lot of parameters. If you get this, then that's great. Let's talk a little bit more about how we're actually going to implement this type of idea. And the main thing that is important in a convolutional neural network, I'll give you one guess what it is in the title. It's convolutions. So convolutions are it's actually the biggest lie about convolutional neural networks is that they're about convolutions, because they're not. So convolutions, some of you, if you're say into electrical engineering or you've done signal processing, you might recognize it. I'm just going to write this out. Don't worry about too much of the notation or something. This is just a little bit of historical details. Yeah, it's kind of like this. This is sort of the symbol for convolution of signals x and w, and it looks something like this. You can write it as the integral. If they're continuous signals, they're like x of t times w of I minus t dt. Or if you're in a continuous setting, it would, or sorry, a discrete setting, it would be something like summation of x of t times w I minus t. Yeah, I mean, I'm not going to get too much into what this means, but it's just kind of the one way to picture it is if you have two signals, what you do is you kind of reverse one, you flip it and you kind of slide them by each other, and this gives you a new thing if you appropriately take the products and stuff. This is, like I said, this is classic in signal processing. But if you're not familiar with it, don't worry about it too much. I'm basically just introducing this to tell you that we don't exactly use convolutions. We use something instead called the cross correlation operator, I guess, if you want to be fancy. Nonetheless, whenever you hear people talk about convolutions in the setting of machine learning, it's almost always going to be this that they're talking about. So just be prepared to know it. But I just want to make sure that you know the terminology, and that's a little bit of a misnomer. And the idea is as follows. So what is our input going to be? Our input is going to be, like before I was just drawing it as a vector or just a one-dimensional thing here. But when we actually deal with, say, pictures, then it's going to be something more like this. You can picture what a picture looks like. It's going to be something like, you can think of it as a grid of numbers, where each element of this grid is going to be a pixel, is going to be 1 pixel, and the value represents its intensity. So for example, here is an example of an image. It's a little bit of a caricature, but something like this. So this is, say, our input. So this is our picture or image that we're looking at. And what we're going to do is we're going to take what we call a convolution. We use the same symbol with what is known as, there's a few different names for what this is going to be called, but this is called, it can be called a kernel. Some people call it a map. Some people call it a filter. I might use filter more often than others, but yeah. So this is essentially just another grid with numbers. So this is essentially all that you're going to be doing when it comes to convolutional neural networks. You have some grid with numbers, and you have other grids with numbers, and you kind of are going to do this operation on them, which I haven't really described yet. But it's very simple. So like, let me just show you the answer and tell you how we calculate it. So the answer, or the result of this convolution, will be the following 2x2 grid right here. And it's going to be something like 19, 25, 37, 43. Okay, so this is what I claim the answer is. How did we get this? So essentially what goes on in convolutional, or in this cross correlation or a convolution operation, what it's going to be essentially, I'll try to describe it in words and then we'll do it a bit more mathematically. You take this filter and you slide it over the input. At each place you slide it over, you take the sort of dot product of it and the filter, and the input and the filter, and that gives you an entry in the output. So let me be a bit more precise. So like this here, these top, what you do to generate the first / the top left element of the output will be you take the inner product of this and the inner product of this, and that'll give you this. So let's just do the calculation, just so that it's totally clear. All you do is take the inner product of the corresponding elements. So 0 times 0 is 0, plus 1 times 1 is 1, and 3 plus 3 times 2, plus 4 times 3. So you can see we just took the dot product of the corresponding, like, you multiplied the corresponding entries of these two, and that gives you, just do it, this is equal to 19, which you see is exactly the value we have here. So that's essentially all it is. That's how you get the top left one. And let's just do one more so that maybe it's totally clear. We'll do the bottom right entry. Whoops. Okay, say this. And then again, okay, I guess I'm going to double color this now. This is not looking too pretty now, but okay, you hopefully get the picture of what we're doing here. So essentially, to to compute the bottom right value, then we just take the sort of multiply in the corresponding entries of the filter in the input, and then add them up to get 43. And that's not too hard to see if you just do it out. 4 times 0 plus 5 times 1 plus 2 times 7 plus 8 times 3. This will be equal to 43, which is, I guess, as you can see, this entry at the bottom right. And similarly, I guess this is the entry at the top. So, okay, hopefully that's clear. You just slide again, just to repeat what I said earlier, you slide this filter over the input, and at each position, you take the, I guess, the dot product of the input and the filter at that position, and you fill in the corresponding entry here. So hopefully do it for yourself and try to figure out where this 25 comes from, basically by taking the inner product of this top right 4 squares with the filter. So make sure you understand that before you proceed. But okay, it turns out that these types of operations, I didn't tell you where we get these filters or these weights from, these filters. Eventually we're going to say that these values here that we learn, that are in this, we're going to learn those. But actually this type of operation is actually something that has been used for quite some time in image processing, in the sense that, for example, here is an example of basically a convolution type operation run over the picture on the left. So this is a picture from the deep learning book by Goodfellow et al. And what was basically done here is it's a very simple filter that was run over this, just a single filter, which has values. It's like a 2 by 1 or 1 by 2 rather, which has two things, -1 and 1. So basically what this does is it takes a pixel and it subtracts the value of the pixel on the left. And what you can see is that this is essentially serves as an edge detector. You can see where the edges of this image appear. Yeah, you can see that it basically draws out the edges of where edges appear in this picture. Yeah, that's about it. And you can imagine that this might be a kind of complicated picture to learn from, but somehow understanding where the edges appear, it can be a very valuable thing. Remember when we were talking about this picture of this panda here, you can imagine that seeing where the edges appear here are very indicative, because the panda has a very specific set of edges which can usually identify it just by seeing where its eyes and ears are, stuff like that. So okay, that's the idea of this convolution operator, or this cross correlation operator, I guess more as it's honestly called. So now we're going to talk about how to actually use these in neural networks. Okay, so let's talk about like what a CNN is. The idea is essentially that we're going to create a neural net, but some of the layers are going to look something like this, essentially. But let's take a step before we get back to that. So our input, as we talked about, will be images. And what will an input being an image be like? Well, these are going to be, we've already sort of seen what a picture, I told you this is like an image, a 2 by 2 or a two-dimensional grid or a matrix. In fact, most of the time, images will be 3D objects. And this might be a bit surprising to you because you typically think of pictures as being flat, but let's talk about why. They're going to be 3D objects. Sometimes you'll hear them referred to as 3 tensors. A tensor is essentially a generalization. Okay, just like a matrix is a generalization of a vector. When you take a 1D vector and make it into like a vector, you can think of as being like just a 1D object, but a matrix is like a 2D object. Well, a tensor is a more general way of referring to these family of things, and usually we just use them when we're in when we have 3 dimensions, like think of a 3D matrix essentially, or more. So yeah, that's the idea that that's going to be the image. And why the 3D? Let's talk about this. Well, there's 2 obvious dimensions. There's going to be the width and height, which is like I said, obvious. When you look at this image, then this is going to be one sort of dimension of it, which is the width, and another dimension, which is the height. Let me be clear, by the way, when we're talking about dimensions, like in terms of like 2 versus 3D, these are kind of different from the dimensionality referring to the number of pixels. But you can think of, when I say dimensions right now, I'm talking about the different axes. We're not really going to refer to these as dimensions much more later in this, but I think the 3D way of thinking about it is helpful, at least in terms of visualizing what we're going to be getting as input. But yeah, it's going to have sort of like a 3D shape. It's going to have a width, a height, and then the third thing is a depth. And occasionally we refer to the depth also as like their channels. In the sense that if we have a depth which is greater than 1, then we'll refer to sort of the ith slice in some sense as a 1 channel. So maybe this will be a bit more sense when I talk about like why are there multiple, why the 3D, why is there depth, why are there channels? Well, the way most images are represented are as 3 pictures. Like any color picture is going to be represented generally as 3 pictures, one which is red, one which is green, and one which is blue. And when you stack them on top of each other, that looks like a regular color image. So most images have 3 channels, R, G, and B. So RGB are 3 things. If we have like 1, so 3 for color, We have one for black and white, because it's just going to be intensity, say something between, say, 0 and 1 for each image, or 0 to 255, depending on how you're representing it. But yeah, there's either going to be 3 channels or 1 channel. For the input, that's just for the input. As we go deeper in the network, so we're going to start off with just an image, which is sort of like a 3D object, which has a width, height, and depth. As we go later in the network to future layers, we're also going to have things which have a width, height, and depth, but they might have, say, a different width, height, and depth, and they might have, say, more than just 3 channels. So just be prepared for that. More than 3. So let's just talk about some example sizes of what type of dimensions might we have. So for example, for MNIST, we have, this is remember the image data set, or sorry, the numbers data set. This is a very small one comparatively, 28 by 28 by 1. Yeah, because it's black and white, and it's going to be, images are 28 by 28. CFAR10 are a bit more challenging, or a bit more sizable. And here we have 32 by 32, and they're colors, so they're going to be RGB. I'll show you pictures of what CFAR10 looks like later. Yeah, so these are just the inputs. Like I said, later levels may have more than 3 channels, like instead of just 1 or 3, they might have more, and usually we will have more. And I'll note that the output, this will be generally a tensor which is of shape 1 by 1 by c, where this is the number of classes. And this is kind of analogous to when we were doing fully connected neural networks. Typically, we would have the last layer have c different neurons, and then we would take a softmax of those c different neurons to find out what our prediction should be. Well, similarly, we're going to have a 1 by 1 by c 3 tensor here, sort of 3-dimensional, but 2 of the dimensions are just 1. And that's going to basically, we're going to just take a softmax of this. Okay, so when we are talking about convolutional neural networks, there's 3 types of, so I guess we've talked about so far the input, or what the shape of things are. So let's talk about what layers look like in a convolutional neural network. There's basically 3 types. The first one is fully connected, which we're not really going to talk about because that was the topic of previous lectures. But the next one is kind of the big one, which is convolutional layers. And then the third one is pooling, which is quite a bit, it's simpler than convolutional. And we'll talk about that briefly as well. Okay, so basically what we're going to do is we're going to use this this picture we had here, this image, or this like idea we had in our head here, where we're going to generate an output of each layer as basically taking a convolution of something like this filter with the input layer. So I'm going to now borrow some images from Stanford CS231N class because they're quite good visualizations, so I thought I'd share them, so credits go to them. So here is an idea of what, say, a single layer could look like. Yeah, so, sorry, let me see if there's something I want to say here. Yeah, I guess this is perhaps it for now. Okay, so basically the way it's going to work is that we have some sort of input here. You can see where this is a 32 by 32 by 3 image, and you can see this is the width, the height, and this is the depth for the number of channels. And what we're going to have is a type of filter, which is similar to what we had before. And this one is, say, 5 by 5 by 3. So let's go back up here. Our input here was 3 by 3, and our 3 by 3 by 1, I guess, and our kernel or our filter was 2 by 2. So this is just a different sized one, which is 32 by 32 and 5 by 5 instead. And all you're going to do is simply convolve the filter with the image sort of as in the same way I described there above. It's the exact same thing. So yeah, maybe you can see better in this next picture. But basically you can see here that all we're doing is you take this filter and you slide it over this input, and you take the sort of dot product at each position it has here, and that'll just give you one single value. One thing I'll notice is that before we were just talking about 1D filters and 1D images, but when you have a 3-channel image and a 3-channel, you also have to have a 3-channel filter, because otherwise it's not clear how you'd take the dot product, because it has to really sort of overlap with the entire thing. So yeah, you're always going to have the same depth in your image as well as your filters in the layers. So, but yeah, you can see how essentially what you do is you slide this filter over and you generate one pixel, one value for each sort of place where this filter lands. So let's take a look at the output here. We'll talk a little bit more about the outputs later. But what you can see is that since this is a 32 by 32 image, and you're sliding a 5 by 5 filter over it, you can see that the output is actually going to be a little bit smaller than we had before, in the sense that it's only going to be 28 by 28. Just to sort of see why this is, like remember when we did this one right here, we started with a 3 by 3 and we slid a 2 by 2 one over it, and it became a bit smaller when we exited. It was only 2 by 2. So similarly here, if we start with a 32 by 32 and slide a 5 by 5 over it, it'll be smaller, 28 by 28. The second thing to notice is we started with a 3-channel image, and we had a 3-channel filter because I said we have to, it has to match. Well, and the thing is we only got as output a 1-channel output here. So that seems like it could be kind of bad in the sense that we started with more information here, but we kind of compressed it in the sense that we don't have as much information here in some sense, like we only got 1 channel out. Well, what you can do is you can just do this multiple times in the following sense. So we did it with this first blue filter here. Well, you can just have multiple different filters within the same layer. This is kind of yeah, you just have another filter which will generate another sort of output layer, another output channel. So you can just have multiple filters to generate a set of output layers, and it'll look something like this in the end, if you do it with many. So you can see here what we did here was we started with a 32 by 32 image, which is of depth 3, which has 3 channels. And by applying 6 different filters, we got a new output, which is 28 by 28 by 6. So yeah, that's sort of the main idea behind how a convolutional network works, just by sort of doing this operation. And this is just one layer. So yeah, you start with one input, you run this convolutional layer, and this gives you the output. So just to kind of take it back to what you might find more familiar, it's essentially this was the input, and that set of things that we had on the right side, that's going to be this level here. So it's not too different. It's just another way of thinking about it, which is more useful here. And then, of course, as you know, once we have just one thing, what we do is we like to stack them together. So we could imagine this is something like what a neural network would look like, a convolutional neural network. You would start with just this, and then you would run, say, conv, and then the convolutional layer, and then you would do a ReLU, and then you would get something that looks like this. And then you can do it again. Say, for example, here we do again a conv layer, and then you do a ReLU, which is entry-wise, and then maybe if you do it with 10 filters, which are each 5 by 5 by 6, you're going to get an output which is 24 by 24. And since there's 10 filters, there would be now 10 things. So it gets smaller but thicker in terms of more channels here, and so on. So that's basically the idea of how how a convolutional layer works. Let's talk a little bit more precise in terms of like some of the things which go into designing a convolutional layer. So let's just say you say, I want a convolutional layer here. And then your network sort of says, okay, you need to specify some things for me. Like, for example, you could already see some of the things. We're going to write this out in a sec, but like you have to determine how big this filter is going to be. For example, we said it was going to be 5 by 5. Is that the right size? Maybe you'd want it to be 3 by 3 or 7 by 7. And this 3 here, you can't choose the 3. It has to be the same as the number of channels of the input, but you can choose this size here. There's other things you can choose, like including how many things. Here we did six filters. Do we want to do more? Do we want to do less? And then there's a few other things, including padding and stride, which we'll talk about. So let's talk about conv layer hyperparameters. Oh yeah, sorry. Let me, before, just to show you something pretty cool before we continue, let me also show you one more picture before we proceed. Just sort of so that you can get a picture for what a neural network really looks like in terms of how it progresses in learning. Here's a pretty cool picture, I think, which shows this is kind of the sequence in here. We start with an input, and then we have a bunch of layers, and then a bunch of layers, and a bunch of layers until we get to the end of it. And we'll have, at the end, we're just going to have something which is maybe 1 by 1 by C, like I said, and then we'll just apply like a linearly separable classifier, maybe like a fully connected layer or just a softmax. It depends what you want to do. But anyway, so like the idea is as you start off early in the network, you can see this is what the activations of the filters look like. They're going to be very simple features. Like when I showed you, what's the way to say this? Yeah, when you're looking at this could be a little bit reminiscent of what we saw here, where you just use a very simple feature here in terms of how to figure out what we did to the first picture to generate the second one here. You can see that it was just like a 1 and a -1. So the intuition is at the early layers, there's going to be very simple things like this, like just edge finders and stuff like that. And you can see correspondingly in these sort of low-level features, you're going to see that these are very simple shapes and pictures. Now, as you go to mid-level features versus high-level features, you can see that they get to become more and more complex. And the sort of higher-level features are perhaps the most complex. You can even see little pictures within them. So it somehow says, as you start off at the beginning of the network, you're going to start by learning simple things, but it's going to get more complex as you stack more layers on top of each other. Good. So that's the kind of picture you can have here. And in terms of I guess one last thing I want to mention before we proceed too much further is like, where are the parameters here? What are the parameters exactly? Well, the parameters are exactly what numbers do you put into this 5 by 5 by 3 filter. When I was doing these examples here, I said, okay, let's just put 1, 2, 0, 1, 2, 3. But what you're going to be doing when you're doing a convolutional layer is you are actually going to learn what is the best value for 0, 1, 2, and 3 instead. What are we going to put here? This is kind of equivalent to when we were talking about these neural networks. You're trying to find which weight to put on each edge. Well, similarly, you're going to find which numbers to put in each box of this filter. Yeah, that's the main idea of how we're going to be learning. So, okay, let's go back to where we were before, which is I was going to tell you about some of these convolutional layer hyperparameters. And these are the sort of things that you need to specify whenever you specify a convolutional layer. And there's 4 things. One is the filter size. And this should be kind of self-evident. For example, like this is a 1 by 1 filter. This is a 2 by 2 filter. This is a 3 by 3 filter, and so on. So you have to specify the width. Well, I guess this is the width, the height. And these are typically going to be square. It's kind of rare that you would use non-square things. So we can just call it maybe, what do I use later? Let's say that this is going to be f. So that's one thing. The other thing that we're going to have, the other things we're going to have to specify is the output depth. And this is sort of equal to the number of filters. So like we sort of discussed, each filter here, this is one filter, the blue one is one filter, the green one is another filter. So you have to specify how many filters you want, and each one will give you a new channel in your output. So you can see that in this example, for example, we had 6 channels, and that 6 filters, which will give us 6 channel output. So that's another thing that we have to specify. Another thing that we have to specify is the stride. And this kind of says how far should you slide your filter each time you do something. So let me just show you sort of a brief example. Let's suppose we have our input, which looks something like this. And suppose we had just a 2x2 filter. Well, then the output is going to look, if we had stride 1, let's say stride 1. Well, what that would look like is roughly, let me just try to sort of paint what this would look like. It would look something like these 4 here would go into this pixel here. And then, sorry, I'm going to have overlapping colors, but these 4 here would go into this. This is exactly what we did before. And let me just show, for example, this one is going to go right here. And you can sort of figure out where the rest are. You can see that you just slide it over by 1 each time. But what about, let's say, stride 2? Let's draw a picture of what, let's draw a new picture for our input here, because we're going to have different colorings. This is our input, and this is still going to be a 2x2, let's say. But if we have, say, stride 2, then the idea is, it's kind of intuitive, as the name suggests, you slide it over 2 each time. So let's see, for example, these 4 here would map to this. But rather than sliding it over just 1, now we're going to slide it over 2, and that will be the next one. So these ones will be over here, and say these ones over here will be this one here, and so on. And you can see, yeah, this is kind of an intuitive idea, but you can see that depending on how big our stride is, you notice that the output image, or the output, the output of this layer will become smaller. So it kind of matters. The higher the stride, then the smaller the output, which kind of makes sense if you think about how stride works here. And the last hyperparameter, so we talk about filter size, the number of filters, the stride, and the last thing that we're going to need to specify for a layer is zero padding. This is kind of counteracting the effects of, say, the fact that things shrink. Well, if we want them to, you'll notice every time we've done a convolution operation, they sort of shrink in size. But if we want things to remain the same size or even grow potentially, which is maybe a bit unusual, but we would have zero padding. So let's suppose, for example, like just to give you a simple example, let's suppose this was our input, and then we had a filter, which is the same size, which is kind of silly, not something we'd typically do. But then this would just give us a single size output because there's only one way to put it. Now, instead, what you could do is you could have a padded input and use zero padding. So what that means is, like, suppose this is the original thing. Well, we're just going to put zeros as the new pixels on the outside of it. And the reason this is useful is because despite these being zeros, it means now the same filter can sort of fit in more places. For example, now you can put it at the top left here, whereas that wasn't allowed before. And this will lead to an output which is kind of this size instead. So you can see we're kind of growing the input by padding it in order to make the output bigger. Yeah, so that's the kind of, these are the 4 hyperparameters which are relevant, which are built in building a convolutional layer. So yeah, I guess I have one more picture to kind of show you. Maybe this is already clear from the discussion so far, but again, I just want to emphasize really, because this is I think not the most obvious thing and a little bit of a technical thing that you have to remember, the fact that you always, whenever you're doing a convolutional layer, each filter will have a depth which is equal to the number of channels of the input. So this is one filter here, and you can see that it's going to have a depth 3 really, and then you just convolve each layer with one of each of the input channels, and then you sum them, and that gives you a 4x4 output like this. Good. So just to really hammer it home, I want to show you a here's another thing also from, I think, CS34 or from CS 231N, which shows the kind of illustration here is showing that this is what you can imagine. Suppose you have a 7x7x3 input with, say, padding equal to 1, and then you can see this is the input here on the left. Yeah, confirm for yourself that the size, I guess the original input was 5x5 by 3, but it includes this 0 padding, so it makes it a little bit bigger. And you can see here is our first filter, which consists of a single filter, but it's sort of depth 3, which is going to slide over it. And you can see that if you take the inner product of all of these, and then you sum them all up and you add on this bias as well, then it'll give you this one little number right here. So it seems like a lot of calculation just for one number, but yeah, that's what you have to do. And similarly, you'd slide it over and get all these other numbers. And then there's a second filter, which you can also slide over, and you'd get this little thing here. Note that this this example here has stride 2, which is why it leads to this size. So just before you proceed, maybe pause here and try to understand why this is sort of right. Maybe do one of the calculations for yourself and see if you can understand why all the pieces fit together. Cool. So let's just summarize. This is basically all there is to convolutional layers. Let's summarize it just sort of in one thing, and we'll also count what the size of the input versus output will be. So conv layer summary. So the input is going to be width 1 by height 1 by depth 1. And there's going to be 4 hyperparameters. There's going to be the number of filters, which again we call k. There is going to be the width / the height of the filters, which is going to be f. Like I said, they're going to be the same, so the size of each will be f by d1, because remember, they always have to have the same depth as the input. Then next is going to be the stride s. And finally, we'd have to have the amount of 0 padding, how many 0 pads we put in, which is p. So those are the hyperparameters, and then we will get an output, which is of size w2 by h2 by d2. But what is the depth? What are these 3 different values here? Well, it's not too hard to see that it's not obvious, let me say, but we can calculate what these values will be based on these hyperparameters here. And I claim that the width of the output is going to be w1 minus f plus 2p divided by s plus 1 at the end. So this is kind of says that I'm not going to do this calculation for you, explain where it comes from fully, but you can see that it takes the input size, and the bigger your filter is, then the smaller it'll get. But it'll also increase if you have some 0 padding. Note this factor of 2 because you put like 0 padding on the left and the right. And then the stride says how many you skip, so like it kind of divides it into that many things, and then plus 1. So yeah, maybe think about it, and you don't need to fully understand this expression, but try to think of how each of the different hyperparameters affects the output size. It's basically the same thing for the h2, which is going to be divided by s plus 1. Basically the same type of calculation. And then in terms of the depth, what's the depth going to be? Well, think about this for a sec. We've talked about it a few times before. There's one hyperparameter we haven't used yet, and that's exactly where it's going to go. the number of filters basically becomes the depth of the output. Cool. So that is and let's, as one final thing we'll note here is number of parameters. How many parameters are going to go into this? Like how many, if you have a convolutional layer with these hyperparameters, how many parameters does it have? Because it'll be useful to compare with how many parameters we would have if we had a fully connected layer. So it's not too hard to see because there are F filters, sorry, there's K filters, and each has how many parameters? Well, each of these is defined by F by D1 parameters. And so the total amount of parameters that we're going to have F squared D1 K weights. And then recall that we also have a single bias for each of them, or yeah, so there's also going to be K biases, one for each filter. So yeah, that's the total number of parameters in this in one layer with these hyperparameters. Good. So that's that. Let's, as one last thing before we move on to pooling layers, I want to do an example computation just so you understand how really efficient, how much we really save by doing this. So compared to a fully connected layer. So, and how many, and what the sizes will be as well. So let's suppose we have an input which is of size 227 by 227 by 3, and we used what hyperparameters do we have for our layer? We have 96 filters, which are 11 by 11 by 3, I guess, because we have to have it by that, and say stride 4, and we have no padding. Well, okay, what is the size of our output? Our output, we have these expressions above, which we just wrote down. The first one, which will be W2, is equal to W1, 227. And what do we have? What do we do? We minus F, which is the width and height of the filter, plus 2P divided by S. So this would be minus 11, because it's 11 by 11 by 3. Then plus 2 times 0, because their padding is 0. Then, like I said, we divide by the stride, so divide by 4, and then plus 1. If you do this out, this gives you 216 divided by 4 plus 1, which is equal to 55. So we start with a 227 by 227 by 3 input, and we have now 55 width. If you do the same calculation, it's the exact same thing for the height. This is equal to 55. And the number of filters was 96, so we have that D2 equals 96. So you can see we went from 227 by 3 to 55 by 55 and 96. So how many parameters do we have here? I want to compare the number of parameters we had here then to compare to how we would do it if we had just a fully connected or a locally connected but with no parameter sharing. So if we just had so how many parameters do we have here? For this layer, we just did the calculation here, F squared D1 K weights and K biases. So that's not too hard to write out. That's just 11 squared times 3 times 96 plus 96, which is equal to 34,944. So that's not, in the grand scheme of things, that's not really that many parameters. It's fairly small. But compare this, and you'll definitely see this compared to if we had a fully connected layer in which the number of parameters is, like we sort of talked about before, you connect all of the things in the input +1 because we're going to have this bias, times the output size. Because you have, you just connect them all up. And if you do this, this is going to be approximately equal to just using this. You just multiply, you essentially multiply all of these quantities together if you ignore the +1, and that will give you something which is on the order of 45 billion. So that is a lot more parameters than 35,000. Now, on the other hand, if you did this in kind of the same structure, that is, what do I want to say? You essentially, you kind of did the same sort of structure, but instead of having the same weights for each filter and like sliding it around, you instead, for the next position, you made a new set of weights there and you had to learn those as well. So if you didn't do weight sharing, you didn't slide things around, you just kept them where they were. Maybe to go to a picture where it's more familiar to you. This one right here, if you just use this one instead of this one, where you kind of use the same weights on same colored edges, and instead you just did this, then let's do the calculation for how many parameters you would have there. You would have there basically it would be number, like, let me say what this is. This is for no weight sharing. And only local connections. Kind of the same structure as we would have in terms of the input to output connections for CNN. And this would be, it would basically, like, I'm not going to belabor the computations here, but it's going to be the number of, this is the number of parameters in one filter. And the idea is each pixel of the output is determined by this many parameters of the input. And so this is the number of this is the output size, which is 55 by 55 by 96, which is equal to 106 million parameters. Cool. So you can see really how beneficial. So just by changing the structure to only local connections, we decreased from 45 billion to 106 million parameters. But by going from no weight sharing to weight sharing, we've reduced it further to 35,000. So CNNs are really much more parameter efficient than the other alternatives. So yeah, that's it for this part. We're going to continue next by talking about pooling layers, and then we'll talk about some CNN architectures.